To truly understand the complex world of macroscopic physics, we first have to establish the absolute baseline rules of physical matter. If you take a solid object and fire it through empty space, it follows a strict, predictable trajectory. It occupies a single, defined location at every moment of its journey. When hundreds of solid spheres are fired through a barrier with two narrow gaps, they travel in straight lines to hit the back wall. Over time, these impacts cluster into two localized vertical bands, the exact signature of particle behavior. We can contrast this exact coordinate-based travel with the continuous flow of things like sound or water. A single grain of sand cannot exist in a state of continuous spread. It cannot physically pass through both gaps in a barrier at the exact same time. The first rule of classical mechanics is strict. Matter travels as discrete, localized coordinates. The second rule set governs the propagation of continuous energy. When a continuous wave approaches that identical two-slit barrier, the solid geometry cuts the single wave into two smaller wavelets that ripple outward and intersect. As these two waves overlap in the empty space, they physically interact. Where two peaks meet, the wave height doubles. Where a peak meets a trough, they cancel each other out, leaving flat water. On a terminal screen, the interference pattern forms a barcode of bright and dark bands. Bright bands show wave amplification. Dark gaps mark exact cancellation. When compared side by side, this barcode is the exclusive signature of waves. Solid objects don't cancel out in midair. Classical physics rests on this binary. Matter acts like bullets, producing two bands. Energy acts like water, producing five. For centuries, these two models were mutually exclusive. We trusted them until we tested them on the smallest components of the universe. When we scale down from macroscopic systems to the subatomic realm, the strict binary breaks. Consider the photon. It is a quantized packet of electromagnetic energy, the smallest indivisible unit of light. If we isolate a single photon and fire it individually toward the exact geometric barrier, we must ask which classical rule set it follows. Because we are firing them one at a time, like tiny solid bullets, the expectation is that they will travel in straight lines and eventually build up the two-band particle pattern. This accumulation graph plots the actual impacts of single photons hitting the backplane one by one. Over time, the individual dots do not form two columns. They build up a distinct five-band interference pattern. This output is impossible for a discrete object following a single path. To form this specific geometry, the single dots must perfectly match the math of the overlapping wave algorithm. The data suggests that for this pattern to exist, the single particle must effectively interact with both slits at once, interfering with its own trajectory. To explain how a single physical particle achieves self-interference, quantum mechanics relies on a specific theoretical framework. That framework depends on superposition. This is a state where an unmeasured entity does not exist as a localized object, but as a probability distribution. Leaving the emitter, the photon ceases to be a rigid sphere. It propagates forward as a translucent wave of mathematical probability, passing through both slits at once. This probability wave divides and ripples against itself, creating the exact geometry of wave interference. This wave isn't made of physical matter. It is a statistical map defining the likelihood of where the particle might be found if we check. That check occurs the moment the wave hits the back screen. A photon does not register on a physical screen as a sprawling wave. Upon contact with the terminal boundary, the probability distribution collapses into a single, exact physical coordinate. When the probability map collapses, the areas with the highest likelihood of impact perfectly align with the bright bands of an interference pattern. This mechanic is called wave-particle duality, the capacity of a quantum entity to exhibit properties of both a wave and particle depending on its environment. Physicists tested this theory by placing a device at the slits to definitively measure the exact path each individual photon takes. This introduces a new mechanical variable into the geometric void. A sensor is clamped directly over the gaps before the photon is fired. The sole function of this sensor is to extract spatial data. It records which specific slit the photon passes through. Introducing this active sensor results in a total shift in the photon's mid-flight behavior. Because the sensor is actively recording data, the photon does not blur into a probability wave. It remains rigid, passing strictly through exactly one slit. Look at the resulting data output on the back screen over time. The accumulation of single dots now forms exactly two rigid vertical pillars. The 5-band interference pattern is completely gone. This is known as the observer effect. Extracting localized data from a quantum system forces its probability wave to collapse into a deterministic physical state. The sensor doesn't physically block the slits or touch the photon. Merely the act of recording information alters the physical properties of matter passing through. The unmeasured state yields a complex wave output. The measured state yields a strict particle output. The universe modulates the physical state of matter based on whether spatial data is being extracted from the system. This experiment is often misinterpreted to suggest that human consciousness or conscious awareness dictates physical reality. That is a flaw in vocabulary. In a mechanical universe, an observer does not require a mind or a brain. An observer is purely thermodynamic. It is any mechanical interaction, like a piece of silicon or a red laser, extracting measurable information from a quantum system. When we synthesize the data from both the measured and unmeasured states, we see a consistent logic for how physical reality functions. The mechanics closely parallel the way a computer rendering engine operates. To conserve processing power and energy, the universe simply does not assign definitive physical properties to subatomic matter by default. The default state of reality is a statistical probability. Matter is left unrendered while it is in transit, existing only as a mathematical potential. A probability wave only renders into a strict physical particle at the exact moment that systemic information is actively queried by a mechanical observer.